In this video, I'll be talking about TCP Interactive Sessions. Interactive sessions have to play by a little bit different rules than bulk transfers because TCP Interactive Sessions have to interact a lot more with the server, whereas a bulk transfer, a whole bunch of data flows typically in one direction, and an interactive session, it's a much smaller amount of data, but there's a lot more back and forth. So examples of interactive sessions are going to be a lot of systems administration stuff. So a lot of Windows administration, like remote registry, computer management, but there's also SSH, Telnet, Citrix, remote desktop. A big one is going to be online gaming. So in these situations, delay is going to be the primary metric that influences performance. Now, in a bulk transfer, latency, the delay of the network, how long it takes one byte to go from there to and back, is not that big a deal. In a bulk transfer, bandwidth is going to be the biggest influence on performance. You want to be able to send as much data in one direction as possible. Interactive sessions, bandwidth is not a big deal because the packets are going to be very small. You're actually sending a very relatively small amount of data compared to bulk transfers, but the rate at which you can send them is what's important. So especially with online gaming, if you click to go shoot your gun or whatever, you want that to happen immediately. And that is those have a little bit different rules to play by. So what I've done here is as a demonstration, I set up a Telnet server. Now, I know Telnet, I'll get rid of it when I'm done, but Telnet's cool because you can really see what's going on in an interactive session. So what I'll do is I'll just simply Telnet into Mindbender. Telnet, Mindbender, login, done. Okay, so there. Now, this demonstration would be rather useless if I didn't start a capture. So what I'll do to get a nice clean capture is I'll use a capture filter. Come on. Okay, and host, Mindbender's IP is 1.10 and port 23 for Telnet. Okay, so now I'm just capturing Telnet. Okay, so check this out. What I'm going to do is just press a key. So TCP will just sit idle. I'm going to go into this later when I talk about keep alives and that sort of thing. But TCP will just sit idle, just like this, infinitely. There is no keep alives in especially these old school applications. It's just going to sit here until I do something. So, like this, I press A, and there's our A. Now, what we have here is the when you press a letter, it generates 3 packets. And I'll show you here in a second, but what I wanted to show you is how delay is measured. Now, in Linux, you're going to be seeing the timestamps option. Now, sometimes I've had mixed results with Windows, and sometimes the timestamp option is there, sometimes it's not, and I have yet to find out why. But in Linux, timestamp option, and timestamp is going to be how delay is measured. How long does it take one byte to get there and then back? It's called round trip time, or RTT, and so in Linux we're constantly taking measurements. Every single packet is going to be constantly taking round trip time measurements. Well, that's kind of cumbersome to look at. What we have here in Wireshark, since I'm capturing from distro, the client's perspective, the way we can easily see round trip time is with the delta column. So I added the delta column, and you should probably all add the delta column. And now this is going to have a round trip time of 475 and some stuff microseconds. So 475 microseconds. So just about half of 1 millisecond. So that's pretty darn fast, but that's typical for my network. My network is typically going to be between 300 and 500 microseconds for round trip time. So what we have here is the key press. So we look down here at the Telnet column, and here's my A. Now this is me pressing the letter A. Now, the interesting thing about Telnet is if we look at it, now the moment that I saw the letter A populate the screen Telnet does not redirect to standard out. What I'm seeing is the echo from the server. So what I'm seeing is, bam, the A. This is the response from Mindbender, the server. So what I'm seeing that got echoed onto my screen is the response. So this is me pressing the letter A, and this is the A appearing on my screen. And the last one is the acknowledgement of that. So let's take a look at sequence numbers. So the sequence number is going to be on destro, end in, let's call it end in 46. Okay, now we have 1 byte of data. So 1 byte, which is the A. And so let me guess, the ACK number is going to end in 47. And that's what we have here. The ACK number is ending in 47. It's kind of interesting how, yeah, I might have confused everyone. But the second packet, the response from the server is acknowledging the first. Now, the interesting thing, a primary characteristic of interactive sessions is something known as piggybacking. So you notice the second packet is actually acknowledging, but it's also carrying data. It's piggybacking. It's pulling double duty. So we have data, which is the 1 byte of A, and it's acknowledging. So, and of course, we always have the ACK flag set. You can see it right here. And the reason why the ACK flag is always set, and I think I said this in the last video, is the ACK flag is always going to be set in every TCP packet. Every TCP segment is going to have the ACK flag set, except for the initial SYN packet. And that's specifically for this ability to piggyback. So if the Telnet server has the ability to acknowledge, but also has data waiting at the same time, it says, well, let's combine them. And that's exactly what it's done here. Now, there was no data waiting from the client, so it just sent what's called a pure ACK. It's also sometimes referred to as a naked ACK, but that's kind of gross. But it's a pure ACK. It is nothing but TCP header. So this final one is just, yeah, it's just nothing but TCP. And you can actually see that over in the info column here is what Wireshark will do is it will display in this info column the highest layer in the OSI model that is available, and the highest layer is layer 4 TCP. Therefore, it's going to show just TCP stuff. No application stuff, because there's no application data actually contained in this segment. Okay, so now interesting thing is notice that there just one key press. This is all this stuff. These 3 packets are just for 1 key press. Now that's not a big deal on my gigabit LAN, but back in the early 80s, that was a lot. So I'm literally sending 1 byte of data, the letter A, to the server, and it's so let's say that this was on the internet, and let's ignore the layer 2 stuff. So we have a layer 3 header, so 20 bytes of IP header. We have a TCP header, so 20 bytes of TCP header, and then the data. So for each segment, we have 41 bytes of stuff being transmitted. So that's kind of a big fat waste. And so you multiply that by 3, that's 120 bytes of stuff to send basically 1 character. So back in the early 80s, that was a problem. Well, maybe it wasn't a giant problem, but these are the kind of guys that even if it isn't a problem, they will foresee it as being a potential problem in the future and then fix it. And their method of fixing this potential problem of just sending a ton of header information per character and possibly causing bandwidth issues, the way they did that is something known as the Nagle Algorithm. The Nagle Algorithm is a way of potentially slowing down TCP, so you could possibly send more than 1 character per in 1 data segment. So, for example, what if I was typing my name, JEFF, and so the Nagle algorithm could potentially let me type my entire name, send it, and then the response from the server is back. And that's saving a lot. So yeah, that's saving 3 whole packets. Not 3 whole packets, 3 times 3. That's saving 9 packets. So that's sending a lot of data. Now the way the Nagle algorithm worked is it was really simple and actually pretty cool because it used round trip time basically. So when you were typing, the data would buffer, and it will not send, TCP will not send that data you were typing until the previous segment was acknowledged. So let's say you typed an A and then you typed a BC. So you keep typing, but that A gets sent until the ACK for that A comes back. TCP is going to sit there and buffer BC. Okay, it's not just going to send A and then B and then C as quickly as possible. The Nagle algorithm slows it down. So it's slowing it down effectively to round trip because it has to hear that ACK back, then send more, hear the ACK back, send more. Now that is definitely a defining characteristic of interactive sessions opposed to bulk transfer, because bulk transfers, I don't want to go down a rabbit hole, but they definitely don't have to wait for an acknowledgement to come back before they send another packet. That's a giant topic I won't talk about right now, later. But yeah, so it's slowing it down basically to the pace of round trip time. Now my round trip time is half of a millisecond. So what I thought would be fun, well, I don't know how fun it is, but I wanted to see if I could actually beat the Nagle algorithm. If I could possibly type 2 characters fast enough, faster than half of a millisecond, and populate 1 packet. So let's see if I can do it. I'm thinking I'm just going to have to kind of mash it. So let's see if I can. Okay, so let's see what I got. So I typed, okay, here, no, 1 single character, 1 single character. Here's another data segment, another one. Come on, you. No, I couldn't do it. Let's try it again. Let's type. Okay, that was a lot. So let's come on. Let's see if I can. Apparently, I cannot type. Oh, there we go. I have one. So I typed a K and an O, probably because I just basically mashed on the keyboard, faster than the round trip time. I typed that KO before the previous acknowledgement was sent. So I don't know. I'd have to look at it. But yeah, the Nagle algorithm is in effect. Now, I'm guessing, I don't know for sure, but most modern applications have the Nagle algorithm disabled. I know SSH does, so I don't have any idea about games or Citrix. But with modern networks, this is not that big a deal. Saving basically the amount of header information you're sending when we have 150 megabit connections is not a problem. But back in the early 80s, this was a concern. Now, okay, anyway, so what we have here, another defining characteristic of an interactive session, let's look at the TCP header, is going to be, notice this right here, PSH, that is the push bit, the push flag. What that is TCP telling the application, which is Telnet D, to not buffer the data and just to send it directly to the application. TCP is saying we're not going to fill up any kind of buffer and we're not going to do any of that. We're just going to send it directly to the application so the application can process it and then send it back. So you're going to see the push bit is going to be crucial when it comes to interactive sessions. You're going to almost always see that. Now, typically in a bulk transfer, TCP will buffer a certain amount of data. Once again, I'll go into that later, but TCP is going to want to buffer. So if there's a chunk missing, it can recover from that missing. It can say, oh, this chunk between these bytes and these bytes will be able to resend just this chunk. So yeah, I don't want to go down a rabbit hole of that because that's a giant topic, but push bit is almost always going to be set here. It's really the key to interactive sessions is just know that delay is going to be huge. Delay. So if you're telnetting to the International Space Station or something, you're gonna definitely see the Nagle algorithm. So delay, of course, is the amount of time it takes to go there and back. Now, the most common method of measuring delay that people don't even know they're usually measuring it is with ping. And unfortunately, ping. Let's see if I haven't pinged anything. Ping google.com. So yeah, okay, so I do have a decimal point. So in my ping, I do have a decimal point. So it does have microsecond resolution to a point, so 30 milliseconds. Now what this is round trip time, but it's measured in ICMP. TCP is very much concerned with round trip time. And so it's always taking these measurements, but that is round trip time. And interactive sessions have to kind of play by the same rules that like VoIP. VoIP, of course, is UDP, but the killer for a VoIP is going to be latency. It's going to be network latency, and the same thing with interactive sessions. Now, of course, TCP can recover better than UDP can, but that's where you're going to see performance problems. So, okay, so I think that pretty much covers everything for interactive sessions. Hope you learned something. Thanks for watching.